Hello everyone, I am Ludo, the SG Program Manager in charge of U-space. Welcome to all of you. Take a comfortable seat. I will now open the webinar with some practical information. So first, yes, good question. Why webinar? Why are we there today? Basically, we want to stay connected with you in that period of time, and we think it would be good to take benefits of the working tours that were planned to be done in Madrid during the WAC. That will be a good opportunity to share the first results we have at project level. So we decided to organize 3 sessions. The first one was this morning. Here, this is the second session, and there will be a last session on the 3rd of April at 10 a.m. So this morning, there was a first session about U-space from concept to reality. The idea was to show the spectrum of the activities from the concept definition to the demonstration. So it was an interesting session from the content perspective. I acknowledge that we had to manage some technical issues. From this morning, we learned a lot. So I really hope that this afternoon session will be better from that perspective than the first one. Regarding this session, taking up the U-space challenge, you will see the presenters. They have selected some challenges related to drones. They will show how the SESAR projects contribute to the development of U-space by proposing tangible and practical solutions. And finally, the last session, that will be not tomorrow, but the day after tomorrow, the aim will be to show you how SESAR, which is an R&D project, is connected to real life, real needs, and presenters will show you, will introduce their demonstration activities and some scenarios that they have used during their projects. So some rules to make the sessions a good time for all of us. You see there is a chat, there is a questions tab. Very important, if you have any questions to the presenters, I'm not speaking to the technical concerns you may have, the questions to the presenters have to be put in the tab. For the people who were attending this morning, compared to this morning, we have decided to make these questions and answers open and visible to everybody. So you will see the questions from the other participants, and you will be able to add your questions. In any case, we will take the time we need at the end of the 3 presentations to come on the questions and to answer to them. So time to time, some answer may come from the presenter during the session, but at the end, we will take the time we need to answer the questions we have. As you will see, at the time of the Q&A session, there will be some polls open. So then you will be able to go to them and to provide us with your answers. We'll do our best to stick to the time, especially for the presentation. As I said, Q&A, we never know if we have only 1 question or 100. We'll take the time to go through all the questions. We'll stop maximum 1 hour after. So, in a few words here, U-space. U-space, this is the solution for safe and secure drone operation in Europe. Its first definition has been agreed in 2017 with the U-space blueprint. Since then, the SGU and its partners work to develop its concept and demonstrate its feasibility. So here you see some figures that are interesting, that shows how the work we do brought together an amazing number of players from traditional aviation, startups, research institutes, universities, drone operators, service providers, airports, and so far and so on, national aviation authorities, civil aviation authorities. So more than 100 entities have shared their knowledge, skills, and resources to make this happen. In addition, we also ensured close cooperation with the European Commission, the EASA, European aviation industry, standardization bodies such as the EOKA, because we are fully aware of the importance to have all these players on board. And here I mention as well Eurocontrol as another example. In parallel to this, the project consortiums did their best to consider to integrate what we name the new entrants, standardization bodies like GUDMA, Drone Alliance Europe, or companies from the telecom industry. So all in all, these figures reflect what has been done, and one of them is the 19 projects we have, And the slide just here is just a family picture to show you all these projects together. Here I will not detail them, just invite you to go to the SESAR JU website for more information. There is one page per project, and you will see their description and videos and documentation. After the definition of the vision in 2017 with the blueprint, it was really necessary to act and to act as quickly as possible. So almost everything was done in parallel with this short period of time. So 2 years for the projects. This was a big challenge for the projects and for the SESAR JU. And I don't speak about the coordination with the regulation and installation bodies that were working in parallel as well. So on it all, this is 10 demonstration projects, 8 exploratory projects, 1 project dedicated to the CONOPS that have been launched. Today, almost all of them have delivered their final outcomes, and the SESAR JU is consolidating the results. In March, you can see here the preliminary U-space brochure has been published. This is a first set of results that explain what the projects are in more details. We plan to update these brochures with more information before the summer. By more information, I mean more conclusions and recommendations, requirements, assessment of the maturity of the U-space services, identification of the R&D needs that are still to be addressed. I said this is a European solution for the drone operations, and because this is the solution for Europe, it was necessary to cover a large spectrum of the geographical possibilities and European characteristics, and we did it. So here you see in blue all the countries that have been contributed to this work and all the type of environments that have been addressed in this, by the projects. As well, we had to consider a lot of operational and technical questions that were floating in the air, such as, can we use a cellular network for the drone operations? Or can we have multiple U-space service providers in the same geographical area at the same time? Or can we use the existing aeronautical information for the drone operations? So we have a large set of questions. Here you see the research topics that we have been addressing with the projects. So my presentation, unfortunately, is just an introduction to the webinar, so I will not dig into the details, just to show you some key findings that come out from the project that we can already share. So I will not explain each of them, just to highlight that the first concept of operation for U-space is ready, that we have demonstrated the feasibility of the multiple service provision, of the foundation services, simple strategic conflict resolution has been demonstrated as feasible, and so far and so on. Now, just some messages that I would like to pass to you, because this is not something that comes from the project, but that comes from me as a program manager, something which is some 3 messages that are important for me as a conclusion of these projects. So the first one is how strong the participation was. Compared to 2017, a strong community has been built. A good example here, you see, this is the last Chorus workshop. The project Chorus has built a community, the U-space community network, which was composed of more than 500 members, and that was the way for us to ensure that the CONOPS is widely accepted. And to continue this work, the European Commission has launched a European Network for U-space Demonstration in 2018, which is a forum to share knowledge and support the work of research bodies such as the SESAR JU and regulatory agencies, including EASA. These networks go beyond the SESAR players and involve more actors and in the important task to develop U-space. A second message that I want to pass is that since the start, we say U-space is a set of services, which is true. This is more than that. U-space is more than a set of services. U-space is an ecosystem. And this is something that we started to consider and that we will have to consider in the future. U-space is a system with dependencies, minimum performance, data, and everything has to be considered. And my last message will be U-space is U-space. Clearly, for sure, we know that U-space and the ATM will have to live together. Yes, interfaces are required for sure. U-space has to learn from ATM. Information management is a very good example. At the same time, U-space has its own specificities. Vehicles are different, infrastructure is different, service provisions are different, missions are different. That's why we have to learn, but to prevent the copy-paste from ATM. So that will be all for my introduction. I again invite you to go to the SESAR JU website. You will find the first U-space brochure. U-space videos will be accessible as well. You will see that for this session, some videos will be shown, and more will come soon. As I said, an update of the brochure, the project deliverables, and so far and so on. I will stop my presentation here, and I will pass the floor to Hélène.
I'm Ellen from Unifly, and we were part of the CLASS project. So the idea behind CLASS was one of the first projects, one of the first sibling projects. We started already in 2016, which in drone technology years is the prehistory. And the point at that moment was the visualization. We know that there are so many drones that are up and coming. We know that they are increasing at an incredibly rapid pace, but we are also confronted with the fact that drones are hard to detect. They're small and they fly in the very low level airspace. So they literally fly below the radar systems that would be able to pick them up. So we risk that there will be conflicts and possible even collisions, not just between drones and other drones, but possibly also with manned air traffic. So at the time, especially in 2016, now today we are almost at the point where we have the European legislation, which will be very, very welcome in enabling the drone services market. But at the time it wasn't there yet. And the point was also, how can you ensure the safety if you don't have such a restrictive regulation, if you are not able to see the drones? So we need to be able that we can ensure a sufficient level of safety. And that is what CLASS aimed to do. So the acronym of CLASS was for Clear Air Situation for UAS. You will see that in the other project names as well. We use acronyms, but you can use any part of the word for the letter in the acronym. And we were part of the Horizon 2020 call. So the idea was to merge existing technologies at a time to build the core functions of an unmanned traffic management system. So the goal of the research there was to increase the maturity level of the existing technologies so that we can use them for the surveillance and the identification of drone traffic. So CLASS was led by Airbus Defence and Space, and they were joined by international partners. So we had Valence, who are now a Thales company. We have ENAC, the French School for Aviation. We have the NTNU, who are a Norwegian university for technological research. And we also have Unifly. We are the leader when it comes to the field of unmanned traffic management technologies. Together, we wanted to see if it was possible to monitor the drone traffic in a given area and also to separate it. So we have seen in Ludovic's slides, we've seen that there is strategic deconfliction, but within CLASS, we focused on tactical deconfliction. So what did the project partners bring to the table? We had Airbus, of course, who besides their knowledge and expertise brought in their tracker. This is a small device. You can't really tell it, but you can see the size of the finger there. So it's not very large at all. And the drones were equipped with this tracking device with the goal to transmit the position and the identity of the drone. So in other words, to make the drones visible, which of course improves the safety within the airspace. Now, secondly, we had ENAC on board who designed the use case scenarios for us. So they figured out how to fly in a way that would be most beneficial for our research. They also did the actual flying of the drones, which is really not as simple as it seems. Here you can see one of the drones that ENAC was using. I also uploaded a small video, which I hope I am able to share with you via this channel. We are about to find out. This gives you a little bit more of an interactive view on what it was like for us. So you can see at the time we are very much, I will say, in the middle of nowhere. We are safely away from people. Here you can see how the drones are being calibrated prior to the flight. So to be absolutely sure that there is no strange things ongoing and that everything goes exactly as planned, before the flight, all the GPS things and all the other things are tested. So there, off she goes. And now while the drone is flying, because as you can tell, they're actually quite difficult to spot. you need an external system that is able to also spot them. So here you can see the Avalent system picking them up. And as you will see a little bit further on in my presentation, we don't just have the location of the drone, they also calculate the likelihood of it actually being a drone. So you see that was a successful landing. For us in the project, a successful landing was if you can reuse most of the drone afterwards. So I will now try and go back to, no, hang on. Oh, I'm still sharing my screen apparently. Hop, oh, I have to select it here. Ah, good, here we are. Excellent. So here you see once again the ANAC drone, which they have built. I think it's quite a very nice one. So I can actually already go to my next video because the next slide is also a video, but it doesn't work so well directly in the slides. Let me go back to my media. Can you see it?
Yes, we do.
Okay, awesome. So I'm going to speed this up a little bit while you are looking at it, because obviously this covers quite a large area. So it seems as though the drones are flying very, very slowly. They're not super fast, but for the most part, you barely see any movement because, well, there is a very large area there to be covered. So I'm just going to fast forward a little bit. Can you see the drone there? It's the small orangey object. I will make it move a little bit. So now you can see the system has picked up multiple drones, and I will make them move just a little bit faster because otherwise we are just looking at drones doing whatever. So you can see the actual path that the drone was following. And this is really, really important when it comes to the safe integration of drone traffic, because if you're looking at a given area, you need to be able, depending on the area, you need to be able to pick up all the traffic that are there. Because typically we speak about collaborative or cooperative and non-cooperative drones, but that doesn't necessarily mean that a non-cooperative drone is that of somebody who has bad intentions. It just means that the drone is not able to transmit its own position, so we need an external system to be able to pick it up. Whereas a cooperative drone is able to transmit its own system, so it can do so independently. But again, that is completely disconnected from the intentions of the pilot. It is perfectly possible to have a non-cooperative drone, but to be very much allowed to fly there. So here you can see a number of drones that are very gently moving across our screen. And I'll take the opportunity to tell you a little bit more about how we work together here in this project. So Avalent is a radar company. They've specialized in holographic technology. So they are able to pick up all types of traffic in a given area and then calculate if something is going to be a drone or if something is going to be a flock of birds or something else. Because obviously all the data that are coming from objects, well, not objects, but things such as birds can be discalculated from our algorithm because we don't need that data. We're not going to take it into account. So the role of the NTNU. So here you can see, I think this is quite interesting. Here you can see a little bit more about the Avalent screen. I will speed it up. So what we did within the project is to include this real-time tracking that we had thanks to the Airbus trackers and of course thanks to the ANAC drones, because otherwise we would have had nothing to track. And then the Avalent data of all the traffic that was being picked up. Then the NTNU created a data collector algorithm, and we displayed everything together within the Unifly UTM. So in other words, rather than having separate screens, the system makes it possible to have just one screen that combines the data from these various sources. So if Avalent is picking up a drone in location XYZ, and we also have a tracker in location XYZ, then the system will calculate if this is actually the same drone that we're talking about and merge this data. So as you can see on the screen, we have a couple cooperative drones. We also have a couple of unknowns. So these are non-cooperative drones. However, if we click on them, it is very well possible that there is an operation connected there. So we still know who the pilot is. So in a nutshell, what we've explored in class was the real-time tracking and display of both these cooperative and non-cooperative drones and the relevant aeronautical data. Because obviously you want to display all the information that you need to know, but you don't want to overload the authority or supervisor with all the data that is available out there, because there is simply too much data, even though today there are not so very many drones yet, they soon will be. So some other things we had in there were geofencing. So in other words, the pilot receives a warning if he leaves the area where he's supposed to fly. Sorry, geocaching that is. And also geofencing is if an area is protected. So if the pilot comes too close to the protected area, that is geofencing. And geocaching is to keep the drone within its cage for extra safety. So in conclusion, the key challenge that we faced within class for the safe integration of drones into the airspace is the need for complete situational awareness at all times. Especially if you look at sensitive areas such as airports, you really see that the drones are a potential threat. I don't have to explain too much about that anymore. Unfortunately, we've seen it already happen. So the necessity to really detect all the air traffic in such a given area is already very clear. And what we demonstrated in class is that it is possible. We successfully combined the technologies that you need to pick up all the traffic in an area, to differentiate if these people are supposed to be there, and to be able in real time to connect with the people who are flying. So together with the sibling projects, we in class, we are very proud to have been able to provide the groundwork to identify and to deconflict drone traffic in a given area. For those of you who will be joining on Thursday, you will see how this work formed the basis for a large-scale demonstration project. Thanks to class, we know where the drones are and we know where they are going. So this is a key enabler for the further development of U-space. Thank you. I will stop sharing my screen and hopefully I will see some questions.
Thank you, Helen. So feel free to start to answer the question by writing. In any case, but we'll come back with all the speakers at the end to pick the questions that are subject to a common discussion. So again, that's a good opportunity to remind to the participant that you can use the questions tab to ask questions to Helen or to everybody. I see already some questions. Very good. I will give the floor to Antidio, who will speak about SAFEDRONE. Welcome, Antidio.
Thank you very much for inviting us to this webinar. Today we are going to talk about some of the highlights of SAFEDRONE project results related to the increased safety of drone operations. So SAFEDRONE is a SESAR demonstration project. The consortium was led by Indra, and then it was composed by CATEC, which is a research center, ENAIRE, which is a Spanish NESP, CRIDA is another research center in Spain, then UniFly, U-space provider, University of Seville, also as a specialist in highly autonomous drones, and the company IAI. So basically, the first set of results that we would like to show is about different strategies that we have tested in order to ensure the separation with manned aircraft. It's important to highlight that separation between drones and manned aircraft is critical for VLLL and long-range flights with drones. It's true that, for example, in rural areas and peri-urban areas, it's probably going to be the main risk and blocking point for the market growth. In these areas, we have a low density of people, for some, and then therefore we have a low ground risk. Also, we will have most probably a low density of drone flights in these rural areas. So then the risk of a mid-air collision with aircraft has to be safely managed. We have developed and tested two different strategies within SAFEDRONE project. They are based on aircraft equipment, could be, for example, DSB, and also ATC communications. And we will explain the different strategies next. So when we have an aircraft, manned aircraft that is equipped with ADS-B of any other broadcasting mechanism to get its position, okay, we can make this detection, then the aircraft is cooperative and the detection is quite easy. In this sense, once we have this tracking information, this surveillance information, we can automatically create a geofence around the aircraft. A no-fly zone. It could be a dynamic no-fly zone, that this no-fly zone automatically, as you can see in the below video, follows the aircraft position. Then the drone operator that are operating nearby will get a conflict with these no-fly zones, this geofence, and will receive the alerts and instructions. And then the operation can be safely performed. So below in the video, you can see the data from one of the experiments that we have performed in SAFEDRONE, where an aircraft is going from right to the left, and you can see how the different alerts are, how the aircraft is getting closer to the drone operation area. You can see how the position is getting from the ADS-B equipment, and how the no-fly zone, the dynamic no-fly zone, is generated automatically. And then the different alerts are transmitted to all the drones operated in that area. The only problem here, as you may know, is that we will need to increase the coverage of ADS-B or whatever other technology in order to get to ensure that we will get this tracking information all over the territory. The second option is what happens when we don't have an ADS-B, an aircraft that is not equipped. And this is not uncommon in private aircrafts or even in ultralight aircrafts. So in this case, the idea is to use the ATC communication and some procedures with ATC. So the ATC knows more or less where the aircraft is more or less about, and if the aircraft is going to enter very low level for landing or for emergency, the pilot directly transmit this information to ATC. And then the ATC, with a tool that we have developed, these Nairo drones that we have developed within the project as some interesting functionalities, will generate a large protection area. In this case, the use of the airspace is a little bit less efficient because we don't know with a high precision where the aircraft is, but we will create this geofence or no-fly zone area that is static. Then the drone operator that are in that area receive the alert and instructions, and then the operation is safely performed. So in both cases, we think that we have seen and do some experiments that it can work. It's true that with the first option, the use of the airspace is more efficient, but you have to ensure that you receive this information through U-space. The second set of results that I would like to comment is about different procedures that we have developed related to no-fly zones under VLL U-space operations. We have tested 3 different procedures. For example, what happens when there is a no-fly zone activation and the aircraft is in this no-fly zone, and the aircraft has to get out of the no-fly zone. How long does it take? What is the best way to do it? The second is what happens if you in an intended way, you get inside a no-fly zone, okay, without wanting to do it, and how should be the procedure to get out as fast as possible to this no-fly zone. And the third one is we did some experiment in order to get some experimental insights about how big should be the alert distance in order to get some alerts before getting into a no-fly zone. So how big should be this alert distance in order to get the first alerts in the operational interface of the drones? So we're going to briefly comment a couple of them. Regarding the intrusion, as I said before, we have here, the idea is that we have a multi-copter drone system that is flying and then is inside a no-fly zone. So we tested the 3 different ways of get out of the no-fly zone: manual flight, return to launch, and sending a waypoint, additional waypoint outside of this no-fly zone. Okay, we tested with a multi-rotor system, and these are the parameters of the tests that we perform. So as you can see in this, okay, you can see here the video. Here you can see the results. As you can see that that here you can see the seconds that it took for in the mean of the different experiments to get out of the no-fly zone. Okay, taking into consideration a manual procedure, a return to launch procedure, and also a waypoint. Okay, as you can see that if we compare both speeds, okay, in general, also the pilots, they were more comfortable taking manual control and getting outside using the interface or the visual interface of U-space. Okay, the second one that was faster was return to launch or return to home, and the last one that it was more a little bit more slower was the waypoint, in order to go to the screen and then define a waypoint, and then the outside of the no-fly zone, and then the UAV automatically gets out of this no-fly zone. Okay. The second test that we did that we're going to explain today regarding these procedures is the alert distance. So we also, when the drone is going to get close to a no-fly zone, okay, how far we should send an alert to the multicopter or to the drone in order to be sure that that it's not going to enter the no-fly zone. Okay. So we did a different number of tests, okay, with different alert buffers parameters, okay. So the idea, we define a no-fly zone of 300 meters up to 50, and then we say, okay, how long should be in the horizontal and vertical plane these alert distances. So we did this test with a fixed wing and also with multi-rotors using these parameters that you can see here. As a result, you can see that we defined that we needed for this setup at least 100 meters, which is 1/3 of the no-fly zone, in order to be sure that the drone is not going to enter the no-fly zone in the horizontal plane. Okay, we did different number of flights, and these were the results that we entered. We know that more results are needed in order to get a larger study, but I think that this kind of number could provide a nice idea for that. Now, the right size or the right magnitude that this alert buffer should have in the future. Okay, finally, the last point is the integration of the detect and avoid system within U-space. Okay, here I'm going just to show, okay, I hope you can see it. So the idea here was the following. We integrated an onboard detect and avoid system. This onboard is based on a 3D sensor. That is a sensor that can provide a 3D map of the environment. Okay, and this, you can see the drone performing a flight within U-space. And then there was an obstacle. There was a building that was not considered in the flight plan. Okay, and you can see here how the multicopter is able to create a map, a 3D map in real time, and automatically is able, using some algorithms, is able to find a safe path. Okay. Then in the project we realized, okay, how we integrate this with, for example, tactical deconfliction parts, and how we integrate this change of the flight plan with all the flight approvals of U-space. So what we find out is that for small changes of the flight path, as here, in order to avoid obstacles like this building and so on, we think that these changes, the flight path could be considered with some marginal errors that allows you to change the path within this initial flight plans that you can move around some margins. Okay, so if the margin is large enough, you can even change automatically this flight path in order to avoid some small obstacles like cranes or parts of the buildings, and it's not necessary to contact U-space and use the service in order to renegotiate this flight plan. Okay. Just to conclude, okay, I'm going just to share my conclusions. Okay, 1 second. Okay, so basically, today we presented the highlights of the SAFEDRONE project. First, we presented a couple of strategies to ensure separation between drones and manned aircraft with equipment on board and without equipment. Then also we also presented results regarding to gain experimental insight about U-space procedures respect to no-fly zones, no-fly zone activation, intrusion, and alert intrusion as well. And finally, we briefly explained the non-cooperative they can avoid of obstacles and how we can integrate that with U-space services.
Thank you, Antidio. I will give the floor to Petre. Petre is a special guest for us because in my introduction, I spoke about the 19 U-space projects, and you will see that if you go on my slides about U-space, you will never find emphasis, because at the start, emphasis is not a U-space project, but here you will see let's say the power of being in a program like SESAR is that we are able to not only work on the topic we work, but as well to use the strengths of the other activities. And emphasis is a SESAR project for sure. It is not a U-space project, but you will see from the content of Pet's presentation that it makes perfectly sense to U-space. So Petre, welcome, and I give you the floor.
Thank you, Udo, and thanks a lot for giving this opportunity to present here. Although, as said, emphasis is not really in the package of the U-space project, strictly speaking. So my goal today is to give you a short overview of the activities and main outcomes of the project emphasis, which were run under exploratory research call of SESAR, and specifically focused on affordable CNS functions for low altitude operations, addressing primarily the general aviation and rotorcraft operations. But as said, this project was focused a lot on the technical enablers, and these technical enablers are, of course, very common with U-space activities. U-space, they are applicable for U-space users, and also this type of users are expecting to interact in the future quite often with the U-space and U-space users. So this creates really the tight link to U-space development and work. So the project was running for 2 years, and consortium consisted of 4 partners: Honeywell. I am representing Honeywell, located in Czech Republic, Airbus Defence and Space, University of Tampere, and Vector. So what were really the challenges that of the today operations that we were trying to solve? I try to explain it based on this slide. So as already said by Ellen earlier today, and also Antidio, the primary prerequisite of any safe operations is that you are visible for all the users. So what we were really looking on are on the users which are somehow between the conventional ATM environment, where everybody is carrying Mod-S or Mod-C transponder, and potentially is also required the ADS-B out capability for them. So basically, this makes the aircraft visible both to the ground surveillance and to the other aircraft equipped with appropriate anti-collision or surveillance systems. On the other hand, we have the new type of users, for which basically the new regulation related to air identification and position reporting is under development. And then we have basically ultralight aircraft, sport aircraft, so a big part of general aviation, and also the rotorcraft, which basically do not have the transponder. These are not drones, so they are somewhere between, and in fact, they represent potentially for both type of user threats, because the only way how to detect them is in fact through the visual contact for manned aircraft, or through some kind of non-cooperative sensors for which the performance is usually lower than on the cooperative surveillance means. So the challenges that we wanted to address in the emphasis project and we try to solve is how to make them visible, how to connect them to the services. So they will fly basically in low altitude airspace. Although they fit somehow in the ATM world, mostly they are operating in uncontrolled airspace, so they have just a very limited set of services based on the flight information service, typically. So how we could connect them basically to the new set of services that will be deployed for the new type of users, and take the benefit from them. And also one specific technical challenge related to the low altitude operations is potential degradation of the GNSS signals. So also how we could handle the degraded GPS or in general GNSS performance. So, and most important, how to make this in an affordable way, as most of these operations are in fact non-profitable or non-profit. So I said that the project was focused on the technical enablers. So what exactly or what specifically we addressed? So we looked how to use the cellular network for positioning. So this was apparently something that was considered both in the context of the navigation, so how to handle the degraded GNSS situation, but also for the surveillance purposes. So if we use ADS-B or any kind of position reporting, the navigation source is of course of critical importance, because it drives basically how useful and how reliable this information will be. We looked how to use the cellular network for data link, apparently primarily to take the profit for the connection of the U-space services, but also of course using this data link for GA specific services that could be deployed based on this kind of infrastructure. From the perspective of the surveillance, we look on the possibility of an affordable low-power ADS-B transceiver for this type of users. So, and I will have more details later in my presentation about this. And when speaking about the affordability, the important part of the cost of any avionics, in fact, are the certification costs. So when operating in a highly connected environment, we also looked what could be the alternative certification means, saying approaches basically how to ensure that the reliable and accurate performance of the system. So this is basically related to the scope of the project. Now I would like to give at least a short summary of some of the outcomes. So first, in general, about the use of cellular network for aeronautical operations. We can say that we had two parts of the activities and results. First, we did a whole bunch of simulations. In particular, University of Tampere used a simulator to simulate propagation of the signals, interference techniques, both for 4G and 5G, and looking what are the driving factors for the performance of the link for the position for the data link. There the results are interesting, because in fact when looking on the 4G definition of 4G standard, we will see that in fact if all the features of all the main features of the 4G technology are really deployed in the infrastructure, 4G technology for a large set of application and services is quite sufficient, even for the aeronautical operations. Of course, under the assumption that there are interference between the different stations are solved. 5G, of course, offers additional benefits, and the performance can be even improved, especially if you combine millimeter wave and centimeter wave channels. So this is definitely a big opportunity for the future. But what we wanted to highlight, in fact, even with the 4G, you can do a lot theoretically. Airbus Defence and Space make a whole bunch of simulations also on the positioning within 4G and 5G, and they come to the similar conclusion. Basically, if we consider the technical capability as contained in the standards and tune the network for this type of applications, we can get to the positioning accuracy which is comparable to the GNSS. Now when we switch to the practical results and when we go to the real measurement in the real network, we discover that there is a huge difference between the two. In fact, it was not surprising. Maybe surprising was how much it is different. There are basically two main reasons of this, based on the discussion that we had also with the telecommunication companies. In fact, current network is optimized to terrestrial users. This is known, and it is not surprising because aeronautical applications of this kind of technology is coming in the last years. So basically, higher you are flying, more you need to solve the interferences and handover between different BTS or different antenna stations. So this is something that need to be solved. However, there are the technical means how to do it, but simply the current infrastructure is not tuned for this type of operation. So if we would like to use it as it is now, there are really the problem of outages. This is not about really the performance, because when you have the signal, when you have the link, the performance is quite good, but there are outages basically in high altitudes. And so, but it could be solved basically if the appropriate interference means are deployed and the network is tuned for this type of usage. What is more important and more problematic is, in fact, all the network providers, at least that we were looking on, deploy only small or bigger part of the 4G features. So and this is really driven by the business case. So in order that they deploy the future, for instance, which we need for the accurate positioning, they would need to see the business case. They do not see it today, because typically users use it just for the assisted GPS. So the network positioning is just helping basically to GPS to start basically tracking faster. It helps a bit in the performance, but there are no really the business case basically to use the infrastructure for the positioning. Similar for aeronautical operations, you would need a different antenna configuration, the tuning. Again, the business case really drives what they deploy. It is not just the fact that it is in the standard, that which means basically that it is deployed in the real world. So I think this is really the big part, and this is also one of the main outcomes or conclusions of our project. That basically we need really the intensive coordination with network providers to work jointly on a business case to make them aeronautical operations attractive, and basically motivate them to deploy the future that we will need. And this is basically common for 4G and 5G. It will be also the case for the 5G. in order that they do not focus only on the big broadband, so faster internet, faster connections, but in order that the support of the aeronautical operations make for them sense also from the business perspective. So this is one part of the results. The second part of the results, as I said, we looked how to make this type of users. So really looking on the general aviation aircraft which do not care even transponder, but even this one who have the transponder, it makes sense to consider how to equip them with the ADS-B, because ADS-B in systems, so the systems which allow to detect the ADS-B reports, is relatively simple equipment, relatively cheap equipment, so you can equip also even the small drone with them, and having all these type of users basically broadcasting their position on the common frequency would increase really huge safety benefits, because it would allow the other users to see them and take appropriate actions to mitigate the conflict. So what basically, there are two things that make the problem in deploying ADS-B for this type of users. One is related that there is a scare that if we equip a lot of users in a low altitude with ADS-B, we will overload the frequency, 1090 megahertz frequency, which is used also by the ground secondary surveillance radar. It is used by transponder, by airborne collision avoidance system. So this is really critical frequency for whole ATM, and overloading it has very severe impact on this. There were a few cases in the past, and it shows really the big problem. So this is one problem. The second is really the cost of the certified and equipment, and probably third is also the power requirement of the standardized ADS-B out. So how we approach the problem, we say, okay, what is really the driving applications that should drive the performance requirement of such kind of system? These users are usually operating in uncontrolled airspace. So even if saying ground has the surveillance data about them, they do not provide them really with the separation management. So is it really that they need to be seen on the ground, or it is what is really the most critical issue? And so we propose the concept that based on the assumptions that it is the air-to-air kind of detection, which should allow the emergency maneuvering of the other users, and this should drive the performance requirement on the ADS-B. Based on this, we propose to reduce the power of the transmitter of the ADS-B message, and also basically by reducing the power, you reduce the amount of airspace that is basically polluted by your broadcast. So basically it at the same time address also the issues of the overload of the frequency. So we verify this by simulations, in order simulating basically dense environment, assuming a lot of users in an area, to verify how much the spectrum is overloaded. It shows acceptable. What we proposed is the power of 10 watt, which means basically the detectability by about 10 kilometers. We make simulations basically showing this is enough to do the emergency maneuvering for the users that fly, for the users and speeds that are typical for this type of airspace. We developed the experimental prototype. We tested it with 2 vectors aircraft. So in order to verify the detectability and verifying the assumption that we took when for the definition of this concept, and then we try to address also the cost in the way that we suggested how we could reduce the certification requirements, so design assurance level for such system as much as possible, and replace it with the real-time monitoring during the operation, so that we can basically ensure the reliability of the system and of the function based on the real-time monitoring rather than by conventional certification of the system itself. So these were saying the activity performed within the project, resulting in the flight test, which was done by November the last year. It shows basically the validation confirm the assumption that we took for the development of such systems. So technically, we do not see really the blocking or problem or any kind of barriers. Of course, this is a very sensitive topic, so further discussion. What is really needed is now to discuss with the regulator whether such type of approach would make sense for the European airspace and mature the concept in order that it is acceptable.
We can discuss about the questions. There are a lot of questions in the list of questions. So welcome back, Antidio and Hélène. So here, I don't think we can. That will be, and already a lot of questions have been answered by some speakers. Here, what I propose to do is to start with, to pick some of them that I feel interesting to discuss together. Even some of you may already have answer to them. So as an example, so I will take, yes, this one, a question about what requirements do you see for manned aircraft, in particular light aircraft, to ensure a safe coexistence in a shared airspace. Almost all your presentation touch this topic in a way or another. Do you see some requirements, and if so, what type of requirements, what type of approach do you see?
Ideally, all the aircraft would have some type of tracker or some type of way to transmit their own position so that the general system can pick them up and the drone traffic can be deconflicted, because it cannot be that manned traffic has to make way or has to deviate from their route to accommodate the drone traffic. But likewise, if the further ahead that you know that something is coming, that you know what the proposed trajectory is going to be, then you are able to deconflict along that trajectory. Another one of the really good questions that I saw there was with regards to dynamic geofencing. So what type of distance would you create a geofence around a manned aircraft to ensure that at all times the drones are able to stay away? Today, we also already see alerting from the drones. So unmanned, manned alerting is already a thing, but I think that is a technology that still needs to be developed further.
I also agree that I think right now the main issue is that we need to make the manned aircraft cooperative, especially for the low level. So I don't know if the technology is one of the existing one, or it should be some kind of network identification specifically for general aviation. But in our opinion, we think that making this type of aircraft in this type of airspaces cooperative will simplify the integration of drone into the airspace.
Just repeat, and also by those considering what I just presented, what we focused on the emphasis. So we all agree that basically the key prerequisite is that all these aircraft are seen by the others. So we believe that, and I think there is also one question whether we consider FLARM or in general other technology. Why we focused on ADS-B? We were thinking we wanted to really maximize the interoperability. So basically, when speaking about the GA aircraft, they can meet commercial aircraft, they can meet the U-space users, the drones. So we see, unless we found that it is really not technically feasible, it would be ideal to look on the technology which is interoperable across the users. Of course, if we see that there are really the blocking points technically or even legislatively, of course, then we should look on the other technologies. But we believe that we could find a way how to do it in the interoperable way. But I think in principle we all agree this is make everybody visible. This is really the key.
Indeed. Indeed, thank you. So before the next question, I will just inform you, for the people who didn't see that the polls have been open, so you can react and provide some answer to some questions. So please go and provide your feedback. You will see there are some interesting questions here. Speaking about questions, I have the next question that I've just found interesting here. This is: do you think feasible in the short term for network operators to commit on positioning service performances?
So is it a question for me or a question for Antidio?
Antidio, you. So who wants to start?
Maybe I can start. So we had a discussion with multiple network providers, also not only within the emphasis but also within the other project. Well, 5G is probably the opportunity to do it. I think within the 4G, it is not probably short-term action because really the business case is not sufficient. As the 5G infrastructure will be newly deployed, it is probably a bit more open to include the necessary elements in order to be able to guarantee the performance. But still, well, I think it depends how many of the users really will be flying. Because I think the competition are the conventional users, and there are millions of the users. So now when we speak about, even if we speak of thousands of the vehicles, it can be difficult. Probably jointly with some other areas, industrial area, which will have the similar needs, it could make sense. So for 5G, I would see the chance. For 4G, I do not see the short-term action.
At least from our point of view, at least the positioning system, if they are not based on GNSS, I think they only be useful for security purposes, not for navigation. I don't think the performance that they are getting right now will allow to navigate drones. It will be just to check that the GNSS position is correct and you are where you are saying that you should be. And then the other main question, if it's also about communication, if they are going to provide some kind of to compromise on the services that are required for the different risk levels. I think it's also an important question for the communication service provider.
Yeah, we saw the same thing within the SAFER project, where we had Proximus, who are one of the national telecom providers, and they demonstrated the usefulness of their 4G plus network. So we don't have 5G yet here in Belgium, but the main idea is to have a separate layer for drone communications as part of their Internet of Flying things, and also to keep it separate from the regular mobile communication so that these two are not interfering with each other.
Okay, so I'm looking for next question. Feel free if you saw a question that you want to highlight to mention it. Yeah, this is a question about, it's true that in your presentation you are very focused on some specific challenges. I see a question about how relevant is the provision of tailored meteorological services via, as an example, SWIM, in order to identify adverse weather conditions which can be a threat to the drones. I would like to extend a little bit the question and maybe to give you the opportunity to show how U-space is an ecosystem and how the services feed them together. So here the idea is, do you see other services that can support your works? As an example, here we see the meteorological services will provide information to you to make this easier. So is it something that Do you see U-space services as a service system of system, or some services will be very, very, let's say, unique and isolated? How do you see that?
Meteorological services in specific or in general? All types of services?
In general.
Yeah, it's all about the data. It is so vital to have this real-time view of what is really going on, because if the drones, between brackets, only see what is in the system. So the richer that the data is that we can put in the system, the more various sources that we can plug in to create a more complete, complex view of the world, the more you are able to do that. And moreover, especially drone traffic, which is very vulnerable towards harsh conditions, that is something that you want to take on board at the moment of your flight operations planning. If you know that your drone is able to cope with a certain set of circumstances, then in the flight planning, you want to be able, if you are planning your flight, you want to set fences, you want to set benchmarks there so that the system automatically feeds back to you to say, okay, if you want to fly there, you can't do it with the fixed wing. You're going to need the quadcopter because there are strong side wings. I'm just giving an example, but that is vital for the I would say the large scale rollout of drone services market.
I think that for the U-space, there is an opportunity to give a unique interface for other type of services. I can think about GNSS status, how the GNSS is for different regions of the country, also communication coverage. So provide all the information that the operator needs in order to ensure that he can perform safely the operation. And since it's a digital interconnected system, it could be, in my opinion, a good platform to extend it with other added value services.
Yeah, I think there is definitely opportunity to handle whether just the needs of the U-space users may be considerably different than what we have in the ATM, and this needs to be reflected both in the methods, basically how the weather prediction is obtained, and then I do not see personally a really big issue in terms of deploying this function later, but in terms of deployment, just considering basically that the scales and the granularity that will be needed is quite different from what we have today in the meteor predictions.
Yeah, I agree. This is hyper local, hyper accurate data that you are speaking about here. So that is going to be one of the largest things to solve there.
There are a lot of questions. A large part have already been answered by the presenters. We will see how to answer to all the questions after the webinars. I think it's time for us to wrap up and to close this session. First, to say thank you to the presenters for their contribution, the preparation of this presentation. Thank you to the participants to be at the rendezvous. A lot of people have been connected for this session, and I'm very happy to see that we did not encounter the problem that we had this morning, or much more or less than this morning. So it's quite a good news. As I said, this is the first time for us to organize such kind of webinar. So we will see how we can continue such kind of activities. It's really important for the participants, not only for this session, but for all the sessions. This is something that we say since the start of the work we do in SESAR. We want to make the SESAR projects useful for the community. These webinars is a way to share the outcomes. As I said in my introduction, there will be, so we are doing the necessary to publish the project outcomes. So when the project's outcomes can be published, I mean, they will be published on the SESAR website, and you will see that the project consortium in general, they did a lot to ensure that the work they do is accessible to the public, and a lot of information will be available. So thank you to everybody. Thank you to all. I don't know if Remy, you want to add something before we close the session.
Just simply that indeed, thanks a lot to all of you, and the replay of the webinar will be made available rather soon. Thank you.
Okay. So thank you again, everybody. Clap, clap for the presenters. And so see you for the next session that will be the day after tomorrow, if I remember correctly. Bye-bye, everyone.
Bye.
Bye-bye, everyone.
Bye.
Bye-bye.
Bye. Thank you for organizing.
Bye.
Welcome.
Thank you. Bye.